Hi, good afternoon. We are the UAV team, or also the UAS team, and we're going to be talking about the scientific applications of UAVs, which is an acronym that stands for Unmanned Aerial Vehicles. I'm Ryan Wicks. This is Seth Engelberg and Todd Beals. We are all in the Sustainability Science program in the Environmental Conservation Department here at UMass Amherst. So right here, as you can see, we have a few examples of UAVs that we've been using this last semester, and Seth will talk a little bit more about them a little bit later. But there's many different applications for UAVs, and so in this slide, we just want to try to showcase some of the many different applications that exist out there. Everything from, military use has been around for a couple decades now, but here we have slides showing use in police work. Amazon has experimented using them for package delivery, and then you can see a picture up there. You have a Phantom on this slide here that shows that can be used for image capture, and then they're very fun to fly, and a lot of pilots use them just for recreation. And there's a competitive racing circuit starting using UAVs and flying from a first-person perspective, where you're actually streaming the video from the air down to the ground and being able to fly just from the video. So our primary interest is using UAVs for surveying and for scientific applications, as I said. So what we usually start with is we identify an area of study. Maybe we're trying to do invasive species studying. We're trying to map foliage, do damage assessment, or something of that nature. So we'd start by identifying an area and then mapping it out. So here in this slide, you can see we'd start with the low-resolution image, maybe a Google Earth image or something of that nature, and then plotting out waypoints that we would fly between to make sure that we're hitting all the points that we want to be able to capture and sample that area adequately. And this is really important to have that plan in place before we start to fly, because you want to make sure you have a lot of overlap between the images that you have when we start to try to analyze the data. It's important to have that overlap, as I'll talk about in a little bit. And so there's a bunch of different mission planning software that's available out there. On this slide, we're showing the interface that's used using the ArduPilot, open source. It's part of the ArduPilot open source software kit. This is the mission planning part. But up here you can see we've been using the DJI Phantom 3, and it actually has an interface that lets us do the mission planning right here on an iPhone or a tablet. And it's able to connect to the controller and link the tablet and controller with the UAV itself. And we can plan the mission out there. So this is an example of a flight plan that was mapped out by Trillium Learning up on the coast of Alaska at a school where there was fire damage. They wanted to survey this area, and you see all those green dots in this slide here. All those dots represent areas spots where they were going to take a picture and take an image. And so all those spots were laid out on top of the image, and then once they were laid out, the pilot knew where to fly to and could actually reference, because the UAV actually carries a GPS on board. It can say, okay, I know where I am relative to this position that I mapped out. So some of you might be wondering, well, if we already have these images to start with, these Google Earth images, why are we even bothering to do this kind of mapping? And the advantage is that you can get these really high-resolution images, 4K images, like the DJI Phantom here. This camera you see on the front is able to get 4K images, which is much better than you can get from satellite photographs. You don't have any atmospheric interference, and you can also get very up-to-date raster images this way. Or digital images, whereas Google Earth might update every couple years, and if you want to, track something on a much smaller time scale, as short as a day or two, we could decide that we want to go out and survey a certain area within a day. We could have the survey done. And the applications here are that you can do species identification and any other kind of surveying that you'd want to do. So here you can see these, in this image, you can see the green and blue dots represent locations where there was an image that was taken, and all those green lines coming down. There's not a green line coming from every single point where an image was taken, but those green lines represent every single image that's able to reference that one point on the ground. And because all those images are geolocated, there's software that's out there. Agisoft is a software package that we've used. Pix4D is another one that exists that's very good. that's a proprietary software package that lets us be able to take all those images and mesh them together. And so this is a point cloud showing where all the images were taken from, and it's able to take each of those images and figure out which pixel, what GPS tag location is each of those images is able to see. And with this information, you're actually able to construct orthomosaics. So this is an example of an orthomosaic that we just took recently, this last weekend, or we constructed using Agisoft, and that we did up in Greenfield. Yeah, using the Phantom, right. And so we flew this pattern. We took maybe a couple hundred images, and then with those images, we were able to run them through the software program, and it was able to produce this raster image, this image that we could load then into ArcGIS or some other mapping software. The other advantage to this process is that because you're taking images from multiple perspectives, and the image itself, the landscape itself is not moving, we can actually, it's like having stereoscopic vision, but having multiple points where you're looking at the same image, and you can actually construct 3D models of the environments that you're surveying. And this can be very useful for assessing things like height in geometry and the shape of, getting more detailed generally. So this is one that we didn't that we didn't survey, but it's an example of just how detailed and how impressive of 3D models you can actually get when you get some really good images. And there's different levels of complexity that you can run, different levels of resolution when you're running this process when you're trying to construct these 3D models in Agisoft. The more complex you try to version of the algorithm you try to run, the more details you can get the 3D model, but it does take substantially longer. So. And with that, this is an example of a panorama of the area that we were surveying recently up in Greenfield. So right around now we just pan to the south. Oh, right. So I mean, you can see you can get some really good images, beautiful shots, just even if you're not doing it for science. You get a bird's eye view that you can't get any other way.
So then this next video that we have playing now, it's the same thing. We took it with this Phantom, except it's more of a mobile shot where the drone is actually moving rather than just rotating around a fixed point. And you can get some really good footage doing that as well. Okay, so let's talk for a second about what it actually takes to fly for that high quality imagery. I mean, when we first started out, each of us had very little experience flying unmanned aerial vehicles. None of us had any experience flying quadcopters. And we first started out going through a training process in which there's a series of levels broken up using some of the different quadcopters you see in front of us. And the point of each of these training levels is to practice your skills in a controlled environment. We would do most of the training inside of a classroom where if you went too high, you would just hit the ceiling and you couldn't lose the drone doing that. And the whole point of that is when you get up to flying something like the DJI Phantom or even a more expensive model, you really want to make sure that A, you don't hurt anybody, and B, you don't lose it and lose your investment. So this model right here, it costs $1,500, and then you have to buy extra props, extra batteries, hard shell backpack. So you're looking around $2,000, $2,500 for this setup versus something like this, it's only $30. So if you break one of those, it's not too big a deal. But if you just start on this and you break it, it's really going to put a big dent in any type of scientific mission that you're trying to accomplish. And the other thing is that these blades, they run pretty fast and they can do some serious damage to yourself or to property if you hit them. So we practice using something that's more benign so that when we go out and we're in the field, we're ready for any type of situation. And we're going to make sure that every single time we get this into the air, we're going to fly it safely and in a way that is actually beneficial for science rather than damaging to human life and property. And on this slide, we have a couple pictures of us actually doing some of the flight training. And part of it is really about developing that teamwork. So in any type of scientific project, but especially in a project that takes technology, advanced technology like this, it's important to have good coordination between team members. So part of the training is about establishing that group communication and trying to get better both in your own piloting skills, but also working together to accomplish a scientific mission. And as I said before, we have challenges broke up into different levels. This one all the way over to the right, actually this one in the middle is called a Hubsan X4, and that's what we're using for level 1. And this one is called a SEMA X5C, and that's actually level 3. The level 2 one we don't have on stage right now with us because it's pretty big. And then this Phantom is getting up until level 5. So in total, Ron Fortunato at Trillium Learning, our industry partner, there's seven total levels, and we've been working up doing the flight training, trying to get through each level so that we can really fly with better accuracy and really get some good scientific missions under our belt.
You want to talk about the gimbal at all?
Yeah, sure. So if you turn that up a little bit, you see that this camera here is mounted on a pretty expensive and pretty high-tech gimbal that uses actuators so that while it's in flight, if there's wind coming in one direction, it actually counteract and the drone will tilt so that no matter what direction and what speed you're flying at, the gimbal will hold the camera straight. So you can be flying pretty fast, or you can be spinning, or there could be heavy winds, and you can still be taking crisp, clear 4K video footage. And I've actually heard of people trying to demonstrate that by flying their Phantom up and having someone just push it, and you start to see the Phantom actually counteracting the person pushing it and the gimbal holding straight and steady. So it's really expensive, really high-tech technology that is integral in our ability to develop these maps and to use the drones for any type of scientific application like invasive species mapping or disaster recovery. If we didn't have high quality imagery, we wouldn't be able to say with high accuracy or precision where the problems really are. But with something like this, we can do it accurately and well. Here's just a little promo clip. That's it. Yeah, that's all we have. Thanks.